Alright, welcome back. We're going to find the continuous time Fourier transform for a couple signals. Here at the left I've got a x of t is equal to e to the minus at u of t, where a is a constant that is greater than 0. And then part b, x of t is equal to e to the negative a times the absolute value of t, where a is a constant greater than or equal to 0. So we're actually going to plot the magnitude and the phase of the Fourier transform of both of those signals. All right, so let's start with A. So if you recall, to find the Fourier transform x of j omega, I need to evaluate the following integral. Take x of t times e to the minus j omega t dt and integrate that from minus infinity to infinity. Okay, so let me evaluate that. So I'm looking at part A right now. So when time is negative, the unit step is 0 and contributes nothing to the integral. So now with the unit step, I can just integrate from 0 to infinity, and then in that range the unit step is just 1, so I can drop it. So I'm going to go integrate from 0 to infinity of e to the negative at, so that's the signal in that range, e to the minus j omega t dt, like that. Now, properties of exponents allow me to factor out the negative t from the exponent, so I have a plus j omega, like this. Of course, I have the integral of that from 0 to infinity dt. Good. And now I just integrate that like I would normally without complex numbers. And so I have minus 1 over a plus j omega, the reverse of the chain rule there. And e stays the same. And just for a sanity check at this point, whenever I take an integral, I like to take the derivative and see if I get back the integrand. So if I take the derivative of my answer, and I need to, from the chain rule, then I need to multiply by negative a plus j omega. So the negative cancels with the negative, the a plus j omega cancels with the 1 over a plus j omega, and I get back the integrand. And so I know I've taken the integral correctly. So I proceed. Stick in infinity for t, and e to the minus infinity is 0. And then stick in 0 for t, e to the 0 is 1, so this becomes minus minus. So that makes a plus 1 over a plus j omega. And so I get the answer, or at least I get the Fourier transform. I'll just remind you this is x of j omega. And that's the Fourier transform of x of t. Okay, so the question asked me to plot the magnitude and phase. So let's talk about the magnitude of that guy. So that's the magnitude of x of j omega. So the magnitude of the numerator is 1, and in the denominator I have a real part a and an imaginary part omega. So I can use Pythagoras there, and this is a squared plus omega squared, square root of that. And that would be the magnitude. And then let's talk about the phase. The phase of this thing, phase of x of j omega, that would be, well, the phase of the numerator is 0 minus the phase of the denominator, and the phase of the denominator is the inverse tangent of the imaginary part over the real part, omega over a, like that. All right, so now we're in a good position to be able to plot these things. So let me do that. I'll plot the magnitude right underneath the magnitude, and the phase right underneath the phase expression. So this is omega, right? Okay, so you pick a is a parameter of the signal. So you just pick an A just to get an idea of what's going on. Then maybe you plug this into your calculator. You should get a good handle of this though without any sort of technology. When omega is 0, then the denominator is the smallest, and so the fraction is the largest. So when omega is 0, we have 1 over the square root of a squared, which is 1 over a, and so that's the maximum right there. That's 1 over a. And then as omega goes to positive infinity, we go to 0. So we have something like this. and when omega goes to minus infinity, because of the square, we still have to 0 like this. That's an even function of omega, right? And I do want to point out something here. When omega is equal to a, so at this point here, a or minus a, since this is an even function, when you plug in a there for omega, you get 1 over the square root of 2a squared. So you can pull out the a, and you get 1 over root 2 times 1 over a. And 1 over a is the maximum, and 1 over root 2 is 0.707, which we've mentioned before. And so this is 0.707 times 1 over a. So that's actually an important point, and this is a similar point over here. That's a important point for this this plot. So I'll just label that there. That's 0.707 times the maximum. So that's where it drops off by a factor of 0.707. And I'm not going to say too much more about that. And then if we plot the phase, maybe you don't know what the inverse tangent of omega looks like. So I'll just, I know because I've plotted it on a calculator. And this thing goes to minus pi over 2 up there. And actually, sorry, not minus. That goes to positive pi over 2 up there, and minus pi over 2 over here. And actually, at A is that important point. At A, we have minus pi over 4. And at minus A, this is an odd function. At minus A, we have positive pi over 4. So that's what the magnitude and the phase look like for this Fourier transform. All right, so I just want to be very clear. That's the answer. Being that this is the first example that we're looking at, I'm going to go a little bit deeper than what the problem asked. And to do that, I want to examine the role of this parameter here, A. Now let's think about that for a second. And let's plot the signal now. So this is t, and this is x of t. So the signal is 0 because of the unit step, and then it decays like this. And this is e to the negative at, right? And it decays because a is greater than 0, so we have a decaying exponential. Now what's the role of that parameter a here? If you think about it, if a were 0, that would be one extreme, right? Or the limiting case when a goes to 0. Then e to the 0 is 1, and this thing actually never decays. It would stay at 1. So the limiting case, as a goes to 0, then the waveform looks like this. It never decays. And another limiting case, as a gets larger and larger, e to the negative infinity is just 0. And so what you get is something like this. It decays really quickly. So a is controlling the decay rate. Okay. Now, in this case, this as a goes to infinity, this is like a high frequency. It's 0, and then it jumps up real quick, and then it jumps back down real quick. So that's a high rate of change there. Okay, so a gets larger and larger corresponds to a high rate of change. And as a gets smaller and smaller, this is actually no change other than, the initial jump there. So a is kind of like a goes to 0 is kind of like a DC signal, right? It just stays constant. Now let's look at our results here. If a goes to 0, that means that this point goes this way. That means, and 1 over a goes up. So as a goes to 0, we would have a graph that looks like this. Okay, this is the a goes to 0 plot, getting closer and closer. So what does that tell you? That tells you that you have a lot of energy concentrated at the 0 frequency, the DC frequency, right? Remember, the Fourier transform is telling you the frequency content of your signal. And so this makes sense. Up here we said the signal doesn't decay at all. It doesn't change at all. And our Fourier transform, we see, gets centered around the DC frequency. right? Now, when a goes to infinity, we have the opposite case. We have a high rate of change in the signal, and over here then, when a goes to infinity, this point goes further out, which means this thing widens. This thing widens up like this. Widens up, and that means there's energy over here in this regime at the high frequencies. Right, so that's how you can start to interpret this answer, what you're getting from the Fourier transform. Anyway, let's look at B. So B looks similar, okay? So we're just going to start with the analysis equation, right? Minus infinity to infinity of e to the negative a absolute value of t e to the minus j omega t dt. And how am I going to be able to integrate an absolute value? Do you know what to do here? And feel free to pause the video if you want to think about it. The answer is that we have to break this up into two integrals. Minus infinity to 0 of e to the negative a absolute value of t e to the minus j omega t dt plus 0 to infinity of e to the negative a t absolute value of t e to the minus j omega t dt. And why did we break that up into two? Well, let's start with the second part actually. Second part, remember we're integrating versus t. So when t is in this range, 0 to infinity, then the absolute value is doing nothing, right? Because t is positive. So now in this range, we can drop the absolute value. And of course, we know how to integrate that. Actually, we just did it, right? We just did it over here. This is essentially the same thing, right? There it is. So we know the answer to that. What about over here? Well, when t is negative, what does the absolute value do? It changes the sign of t. And so we can still drop the absolute value if we change the sign to positive. Right? Okay, now I will use the properties of the exponent. So I'll just group these together. I'll factor out a t, and I've got a minus j omega. And this one we've done already. So you can look at the steps, and this one comes out to be 1 over a plus j omega. So that's the answer to the second piece, right? Okay, so let's do the first piece now. Let's integrate that guy. So I need a 1 over a minus j omega there. E to the t a minus j omega integrated from minus infinity to 0, and then I've got the one that I've already done. Okay, and again, sanity check. Let me take the derivative, see if I get back the integrand. So from the chain rule, I multiply by a to the minus j omega. That cancels with 1 over a to the minus a minus j omega, and so yes, I get back the integrand. So now I will plug in 0. E to the 0 is 1. And then when I plug in minus infinity for t, e to the minus infinity is 0. So that's the answer to that integral. And then I've got this guy. Not to be outdone, this guy's hanging around still. Right? Okay, so that's the answer, but we can simplify this a little bit. We note that they are complex conjugates of one another. And so I can get a common denominator of the multiplication of those two things. So this actually works out really nicely. If I multiply the first guy by a plus j omega over a plus j omega, right? Just getting a common denominator, and then the second guy by a minus j omega by a minus j omega. Right? Then I have the common denominator. I can add the numerators. So this makes just a. That's awesome. Or 2a actually. 2a. The imaginary parts cancel, which is nice. And then what's the common denominator? Something nice happens when you multiply a complex number by its complex conjugate. The cross terms cancel. So I get a squared plus omega squared. The cross terms cancel. I'll let you verify that. And so this is the answer. That is the Fourier transform of our signal. Okay, now let me plot that, since that's that's the question, right? That's ultimately the question. Plot the Fourier transform. Now, this thing happens to be real. It's purely real. There are no j's hanging around there, right? So, I mean, I can plot the magnitude and the phase, but the phase plot is going to be trivial, being that it's real. So this is omega. Okay, no matter what value I plug in for omega, this thing is positive. This whole expression is positive because we said that a is greater than 0. So 2 times a is positive. A squared is certainly positive, and then omega squared will be positive. So this whole thing is positive, and what I get when I plot it, a similar argument from the previous one, it looks something like this. Okay, and the phase then, being that this is a real number, or a real expression, the phase of that, and it's never negative, so the phase of that is just 0. So that's kind of trivial. This is the phase. And by the way, why is this purely real? So just a little bit of foreshadowing when we get to properties of the Fourier transform. The reason this is purely real is because the original signal is even. It's even. The absolute value is an even function. So an even signal leads to a purely real Fourier transform.